Look at an industrial solar array baking in the sun. To keep those panels from overheating and failing, engineers rely on the wind, specifically the principles of external forced convection across a flat plate. We calculate that cooling using Newton's law of cooling. The equation is straightforward, but the heat transfer coefficient, little h, is notoriously messy. It depends on a chaotic mix of fluid viscosity, density, thermal conductivity, and velocity. To make this manageable, we group those variables into dimensionless numbers. The result is the Nusselt number, providing a clean power law relation based primarily on Reynolds and Prandtl numbers. Finding the heat transfer coefficient is really just a search for the correct constants, C, M, and N, for your specific geometry and flow. Since fluid properties change with temperature, and the temperature varies from the hot plate surface to the cool free stream, we have to evaluate those properties at an average. We calculate the film temperature by adding the surface temperature and the free stream temperature, then dividing by 2. As fluid moves along the flat plate, the Reynolds number increases with distance x. Eventually, it hits a critical value, generally accepted as 5 times 10 to the 5th power. At this point, the flow begins to transition from a smooth, laminar state into turbulence. This graph charts exactly how the local heat transfer coefficient reacts to that transition. The coefficient drops steadily along the laminar section, but the moment transition begins, it spikes upward, settling at a much higher value across the turbulent regime. This diagram illustrates the physical reason behind that spike. In the turbulent region, chaotic swirling structures actively mix the hot and cold fluid layers together. This mechanical mixing pulls heat away from the surface much faster than parallel laminar flow ever could. Identifying whether your flow is laminar, turbulent, or a mix of both is the single most important step before you select a calculation model. Those standard rules work well for air and water, but if you are cooling a nuclear reactor with liquid metals, their extreme thermal conductivity requires a different approach. For highly conductive fluids, engineers use the Peclet number, which combines the Reynolds and Prandtl numbers, and apply the Churchill and Ozoe correlation. This single equation is robust enough to handle all Prandtl numbers. Let's test this framework. If you have a flat plate with a total length Reynolds number of 8 times 10 to the 5th, what flow regimes are present, and do you need a local or an average equation? This chart provides the answer. Because 8 times 10 to the 5th is past the critical transition point, your plate experiences both laminar and turbulent flow. To calculate total heat transfer, you must use an average Nusselt equation that accounts for both regions. Use local coefficients when you need to pinpoint the exact temperature at a specific spot. But to size the actual cooling load for the entire system, the average coefficient is the only tool for the job. We also have to account for the physical boundary condition of the surface itself. An electronic component might maintain a uniform temperature, but an industrial strip heater outputs a uniform heat flux. Under uniform heat flux, the surface temperature actually varies along the length of the plate. This changes the math. Heat transfer coefficients run 36% higher for laminar flow and 4% higher for turbulent flow compared to the isothermal case. Because the heat flux is already a known constant, your goal shifts to calculating the local surface temperature at any given point x. Pulling it all together, every flat plate convection problem follows a strict 5-step sequence. Calculate the film temperature, look up your fluid properties, determine the Reynolds number to check for turbulence, verify your boundary condition, and finally, select the matching Nusselt correlation. Following this systematic sequence, you move from raw environmental data to precise, solvable thermal management calculations.